Section 2.3 is our last section in Chapter 2, which means that we're not too far away from a test coming up. Don't freak out. We've still got a little bit, but this is our last section before the test. We're going to talk about other set operations in this section. We'll finish about probably 40% or so of this today, and then we'll finish the rest next time. So the first set operation we're going to talk about is intersection. So a set intersection is the set of all elements that are common to both sets. So you kind of want to think about what we mean by the street intersection. All right, so think about over here at Kickapoo MacArthur. The streets cross. The intersection is the crossing place, right? It's the dead center of it. It's not the parts that are extending beyond it on each individual street. It's the part where they cross. And notationally, for these two sets, an intersection looks like an upside down U. Or you can think of it as looking at, like, you know, if you did a lowercase n, kind of looking like an N for intersection, if that's helpful as a mnemonic device. Because we've been working on set notation, I'm going to write the set notation for this. This is the set of all x, such that x is an element of A and x is an element of B. Okay? In other words, it's simply among the both descriptors, whatever those descriptors are. Right? So like if I were to describe to you, we'll use biology as an example. If I were to describe to you my biological family, and my husband were to describe to you his biological family, we share a daughter that's ours biologically, so she would be the intersection. But like my parents aren't part of his biological family, and his parents aren't a part of mine. So there's some items that are in both, right? Those are the pieces we're talking about for intersection. It's in both descriptive phrases, whatever they are. The Venn diagram picture for this, because we talked briefly last time about Venn diagrams, though we haven't done much with them, is a rectangle with two overlapping circles. So you have the circles that look like this. So it almost starts to look like, like the Olympic rings or something like that. And these are the sets A and B. And then the intersection is the overlap. It's this piece here in the middle. Kind of bled a little bit into my circles, but forgive me for that. It shouldn't be. That's intersection. The next one is the set union. The set union is the set of all elements that are in one set or the other or both. The notation actually looks like a U, so that one's easy to remember. A union B. This is the set of all x such that x is an element of A or x is an element of B. Again, it could still be an element of both, but the word or that we use in mathematics is not an exclusive or. Exclusive or means it could only be the first one, only be the second one, and there's no including the overlap. When we're talking about this or, it's the inclusive or. It means both is optional as well. So even though the word both is not written, it is an option. And again, if we're thinking about a picture for this, let me make this a little bit thicker. We have that same overlapping circles I drew before. We have the same A and we have the same B. Instead of just shading the part that overlap, you shade everything that's in either circle, including the overlap. You get it all. So a really good descriptor of this, if you want to write yourself down a little note, is union, meaning like marriage. Okay? So when you get married, the words of the preacher usually include something like this. For better or worse, till death to us part, and they have some things here, and it's about the fact that you're joining together, and you might do a unity candle, or you might do these sand things, or there might be a braided whatever. It's all about the fact that you're coming together, and it's all combined now, right? Which means if anybody has any kids, now you both got kids. And if anybody has any debt, now you both have debt. And if anybody has any money, now you both have money. Agreed? So joining together of all the resources. So this union idea is a good description, or a good mimicking of what we talk about when we're talking about getting married. Okay? So this is union. So we're going to do an example of a couple of getting married who do have some kids in a minute here. There's one last one to do before that, and this one's called the relative difference. So the relative difference is the set of all elements in one set that are not in the other. So this one is A minus B. That's how we're going to write that. And it doesn't mean subtraction, but it does have the idea of removal. So this is the set of all x, such that x is an element of A, but it's not an element of B. So picture-wise, if it's in circle A and it's not in circle B, we have this sort of moon-looking shape out here. And a really good idea, sort of to think of in terms of context to remind yourself what this one means, is the idea of a prenup. Okay, you know what a prenup is? Okay, so a prenup is something that people will sometimes get when they get married, and it's usually situations that are extreme, you know, like one person has absolutely nothing and the other one is like a multimillionaire kind of thing. So it's supposed to be safeguarding in such a case that somebody's like marrying you for your money kind of a deal, okay? So I'm not advocating doing this, but it's still a pretty good description of this scenario. So the A part that I've shaded in blue would be like the stuff that you brought into the marriage, and it's the stuff you get to take out of it if you leave. Right, it's the millionaire's sort of, you know, like nest egg that doesn't get touched by the other person if they turn out to be, you know, just a gold digger. Okay, so it's the stuff that you brought in that you get to leave with. Anything that's in the joint pot in the middle gets split in the case of like a divorce situation. But anything that you came in with, you get to leave with. Okay, so we're going to do an example that's a little bit happier than prenups. People are getting married. So Mary is a single mom to one child, Mark. And Joe is a single dad to two children, Jack and Jill. Mary and Joe get married, and together they have two more children, Ann and Andy. If M describes Mary's kids and J describes Joe's kids, we're going to find and describe the following. And if it helps you here, we're talking sort of like biological kids so that we can do this and make sense of the pieces, okay? So what, you know, the kids that they have biologically, you know, had. All right, so the first one, M intersect J. The first thing we're going to do is we're going to simply describe what that is. What does the intersection mean again?
What they have in common.
What they have in common. So actually, I'm going to write that. I'm going to write kids in common. In other words, in this situation, kids that have Mary as their mom and Joe as their dad, right? They're the kids that don't go away on the weekend to spend time with another parent. The ones that just stay put, okay? Who would that be?
Ann and Andy.
Yep, that would be Ann and Andy. What would the union be descriptively? All of them. So in some sense, this is like the family picture, right? You get a picture of the family. Everybody's included in the picture of the family. At least that's what we try to do in my house. It's a chore. There's a lot of people. Okay, the family picture, it includes all kids. So that certainly includes Ann and Andy, so we will list them. Who else does it include?
Mark and Joe. And Jack and Jill.
Careful. I think just Mark. Joe's the dad.
Oh.
Mark and then Jack and Jill. Is that right? Did I remember that right? See that right? It's all the kids. Okay, so what is M minus J?
Just Mark.
Yeah, these are the only Mark kids. In fact, another way that you could describe it is Mark's before marriage, right? They're Mark's kids that he brings in.
Well, Dad.
It was Mark that was Joe the dad's.
Joe.
Sorry, Mary is what I meant to say here.
I was just saying Mark was the older one.
Yes, sorry, I totally wasn't getting my people right. Mary. So only Mary, only Mary's, or you can say Mary's. We'll say before Joe. before Joe came around, this was who Mary had with her, right? And it would be simply Mark. And again, we're talking about a set, so we'll put it in curly braces. Just Mark. Okay, so in other words, divorce happens, heaven forbid. Ann and Andy still have joint between mom and dad, right? Like they still go back and forth. Mark probably doesn't. That's usually the way these things work. It's truly tragic. I mean, I don't know if any of you have experienced that, but I have a niece who did. She grew up with her stepdad, and then there was a divorce situation, and so her brother and her sister went and saw the stepdad because they were his kids, but she wasn't. And so she kind of lost touch with them. But yeah, so this would just be Mark. All right, so a few properties of these sets before we finish up for today. These sets, that is particularly the ones that are union and intersection, have a couple of properties that are familiar to you from numbers. The first one is called the commutativity property. So for all sets A and B, if we do A union B, it's the same thing as doing B union A. Or if we do A intersection of B, that's the same thing as doing B intersection of A. And if you think about the pictures, let me flip back over to the slide that had my pictures on it. One more back, sorry. That should make sense. The overlap is the overlap. It doesn't matter if I have A first or B first. The joining of together of the two circles is the same joining together of the two circles. It doesn't matter if A's first or B's first. Makes no difference. So that's commutativity. The order doesn't matter. Associativity also starts out with for all sets, but we need three of them. So for all sets A, B, and C. If we do the intersection of A and B, and then do the intersection of C, it's the same thing as intersecting A with B intersect C. And it's the same true for unions. So A union B, and then union C. We could have done the unioning in a different order. And we could have done, oops, no parenthesis there, A, and then union B, writing the wrong ones, union C. So the groupings of things doesn't change what ends up getting shaded either. The same portion of the graph is the same portion either way. There's a distributive property. So the distributive set of the distribution of set intersection over set union looks like this. So for all sets A, B, and C, just like the last piece, if we do the intersection of A with B union C, this is the same as the intersection, oh, that's a funny A, the intersection of A with B, and then unioning that with the intersection of A with C. So distribution, it kind of feels like this piece is sort of going over the parentheses, right, and being grouped with each of them individually. That's the distribution property with numbers that we have seen, and will see in chapter 3 too. Okay. You're like, okay, whatever. We'll see how it's used. It's all good.
Probably simpler once
It's okay.
once used, but
All right, here's the last one. This one's actually the last one of the properties, anyway. Talks about the number of items. If you do the number of items in the union, all right, so that's the picture of the shading of the two circles, completely all shaded in blue. This is the same as the number of items of the set A, plus the number of items in set B, and minus the number of items in the intersection. And this one has a really good picture to go with it, so I can show you what it's talking about. It's actually quite intuitive when you see it picture-wise. So here's set A, here's set B. So I want to shade in everything in those circles. That's what the union part is. But the right-hand side says is that if I shade in circle A, like this, and then if I shade in circle B, like this, then I double counted the part where they overlapped. Do you see that? Well, that's bigger. I mean, that's more, think about like area, right? If the area of the left-hand side is 3 and the area of the right-hand side is 3 and I add them together, that's not the area of all this because part of it was double counted when they overlapped each other, right? And so we have to remove the overlapped piece once. So that's what you're seeing happening right here, is the removal of the overlap. So you subtract off the part that's in the intersection one time. Okay? So A is not just the exterior part of A, it's the overlap part of A. B is not just the exterior B, it's the B with the overlapping part of B. And since we've overlapped in each category, we have to remove one of the overlapping pieces. Okay, we have one more thing to write down and we're going to pause. You ready? Last thing to write down for today. This is one more set operation. This is called the Cartesian product. This is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. In an effort to show you what this looks like, we're going to create a couple sets. A is going to be the set X, Y, Z. And B is going to be the set 1, 2, just for the sake of seeing that we can combine pieces and not lose track of where they came from. So letters in the first set, numbers in the second set. So what the Cartesian product says, so A cross B, is that I make an ordered pair so that the first piece comes from the first set and the second piece comes from the second set. So I grab an item from set A and I grab an item from set B and I join them together. Right, so this is kind of like what I was describing last time in class, where I said, like, when I was a child and we would go over and we'd hang out with our friends, they had the same number of kids, we'd join one child, in family hands. Well, we weren't the hands, we were the Chirons at the time. I was not married. One member of the Chiron family and one member of the McCool family, and we'd have a person to play with. Right, so we're joining one from each category. But that's not the only joining that could have happened. I could have joined X with person 2, right? That would have been another possible joining. I could join person Y with 1 or Y with 2. I'm just listing all the pairings out. Or I could have done Z with 1 or Z with 2. And take a look at what happens when you do this. How many items are in set A? What is it? Count. Thank you. 3. Yes, 3. How many items are in set B? 2. How many items did we find in the cross product at the bottom? Sorry, the Cartesian product at the bottom. There were 6. What does it look like happened? Yeah. Now that's only the counting part of it, right? That doesn't create the sets. But it does seem to match with this counting when we're counting what's going on. So if I multiply the number of items in group A or set A with the number of items in set B, I will get the number of items in the Cartesian product A cross B. That is a fact that will always happen. We'll come back to both of those pieces of information, this idea of counting and the idea of listing, next time.